Hello and welcome to this 12th lecture. So in this lecture we will study regarding the capacity of the channel. So we have seen earlier that when the information is transmitted through the channel due to the noise introduced in the channel, there will be some errors when the information propagates through the channel so that what you transmit need not be same as what you receive. Today, we will see what is the capacity of a discrete memoryless channel. So, capacity of a noisy discrete memoryless channel is defined as the maximum possible rate of information transmitted through the channel. So, we have seen what is maximum the rate of information. So, maximum information rate is nothing but the amount of information generated multiplied by the entropy, right? So what amount of maximum data we can transmit to the channel, that is the capacity of the channel. For example, when you consider a wireless channel, it has some capacity to transmit so many kilobits per second or megabits per second and so on. Or if you consider wired channel, then it has some capacity. So we are trying to understand what's the maximum amount of data bits that can be carried through the channel every second. So that's the capacity of the channel. So we define capacity by the notation C, that is nothing but the amount of information, that's the rate of information dt that can be carried through the channel for all the probabilities of input. And we will be choosing one that is maximum. And we have seen how to represent dt. dt is nothing but entropy by considering the conditional entropy multiplied by the rate of information that is generated and inserted into the channel. So dt is expressed here, and maximum of dt that we are choosing. So basically, what's the meaning of this term? C is equal to maximum of dt for all possible values of px. So we will be transmitting some input symbols that is indicated by the random variable x. For example, in case of a binary source, we send zeros and ones. So when you send 0, what is the probability of that? Based on that, you get some value for dt here. And then if you want to send 1, it has a probability. Then what's the value of dt? You get some value. So maximum of those two cases of x, and you get some values for dt. So that is the capacity. That means let us assume that 0 is transmitted with a probability of 0.4. Then you have some value for dt, because dt is nothing but entropy. When you know the probabilities, you can find out the entropy, and also if you know the input rate, then you can find out dt. You get some value for capacity in that for that particular value of x, probability of x. And next we will assume that you will be sending 1. The probability of 1 here may be 0.6. In that case, you find a value for dt, right? Based on this. So that is the second value of the information capacity of the channel. So we will be choosing maximum out of these two. For when 0 was transmitted, what was the capacity? When 1 was transmitted, what was the capacity? And we will be choosing maximum. That actually becomes the capacity. Okay, so here the maximum is with respect to all possible probability distributions for discrete random variable x. That is why we have written here px. So this is basically maximum of dt for different values of px. So that is the explanation here. Because we want to choose the maximum. If when you transmit 0, what you get at the output rate of information, and then when you transmit y, what you get at the output. Out of these two, what is the maximum rate? That is the actual capacity of the channel. That information is the maximum the channel can carry. Okay, now let C be the capacity of the discrete memoryless channel and H be the entropy of the discrete information source that emits RS symbols per second. And now we have the main condition here. If H multiplied by RS, H multiplied by RS is the average rate of information. If that is less than or equal to C, that is total average information rate is less than the capacity, then there exists a coding scheme such that the output of the source can be transmitted over the channel with an arbitrary small probability of error. So that means if the capacity is more than the amount of information that you generate, of course, you can transmit this data through the channel. Maybe there is some probability of error because you have enough capacity to send this data. Your data generated is less than the capacity. Of course, you can send it, right? This is just like you have a pipe having some capacity to send a liquid, maybe water. The amount of water is less than the capacity of the pipe. Of course, then you can send the water through the pipe. Similarly here, this is the capacity of the channel. Channel has a capacity of maybe 1 Mbps. Then your data generated is up to 1 Mbps. Then it's okay to send it to the channel. It is not possible to transmit the information at a rate exceeding C. So if you send the data more than the capacity of the channel, then it is not possible to transmit the information at a rate exceeding C without a positive frequency of error. Now we will move on to the term that is mutual information. So how to represent the mutual information, and also we will see some properties of mutual information in the coming slides. So here, given the channel output y, y is the random variable that represents the channel output, and the channel input is represented by the random variable x. We have a source that emits different informations or alphabets maybe or symbols, and that is represented by the random variable x. And when it appears at the output of the channel, we represent it by a variable y. And let y and x be obtained from the output and input alphabets y prime and x prime respectively. That means the actual symbol transmitted at the input is x prime, but due to noise in the channel you get an output as y prime. Okay, these are the actual symbols what you transmit and what you receive, but these are represented or indicated by the random variable x and y respectively. So here x prime and y prime are the symbols, and x and y are the corresponding random variables to indicate their values. Okay, now the conditional entropy of x selected from the alphabet x prime. What's the conditional probability of x prime? Given that value of y is y prime, that means you know the output is this particular symbol y prime. Then what is the conditional entropy of input? How do we represent that? We represent in this way: the conditional entropy H, given the output is some value yk, the output symbol is yk, then what's the conditional probability of the input x prime? You get some output, maybe you get an output as a 0, then what was transmitted? What's the conditional probability of the input, whether input was 0 or 1, right? So what's the conditional entropy of that? How to represent that? That is equal to probability of this log of 1 by probability. So basically probability, I mean conditional probability here of input log of 1 by conditional probability of input for a given value of output, right? This is how we represent entropy. So in this case it is conditional entropy, but we have the general format of entropy. Entropy is nothing but probability multiplied by log of 1 by probability. So but here it is conditional probability, conditional entropy, so we consider the conditional probabilities here. Okay, so here the random variable takes the values from h of x prime for well-known value of y as y0 or y1 and up to all possible values for output. That is, your output may be 0 or your output may be 1 or something else. If it is not a binary case, then what's the condition probability of input? X prime is what? That means you already know what is your output. Now you are expecting what was the probability or conditional entropy of input. You got this 0 for this value of input, or you got 1 for this value of input, and so on, or you got some other symbol here for this particular value of input. That's what is represented here, and their probabilities is p of y naught, y1, yk minus 1. That is, the probabilities of y0, y1 are given. Then you will be estimating what's the probability of x, that is input. So that's the conditional probability. Okay, now the mean value of conditional probability of x x prime given the output. For the output alphabet y prime is, how to represent that? That is entropy, it's a conditional entropy of x prime when we know the value of y, that is y prime. So how do we calculate that? That is nothing but for all values of y, that is the output, entropy of x prime given the values of y. So here y value is equal to yk. That means k varies from 0 to k minus 1. So here the meaning is your output can be 0 or 1 or any value if it is not binary. If it is binary, it is 0 or 1. Then what was the value of x multiplied by the probability of yk? So this is how we represent the conditional probability. We have seen in the previous lecture. Okay, we will represent it in a other way. So here we have this term k minus 1 and we have j varying from 0 to j minus 1, that is for the input. So now we have probability of input log of 1 by probability of input multiplied by this term. Okay, so this is from the previous point that we mentioned here. Okay, so this gives us the entropy, condition entropy of x prime provided the y prime. So condition entropy is here again. We have the same term here as well as here, these two summations. That is, this is for the input and this is for the output. What are the different values the input can be assigned? What are the different values for the output we can observe? Probability of xj yk here. This is a joint probability. We are shifting from the condition probability to joint probability. Log of 1 by condition probability of xj yk. So this is basically from the base equation. So now here, how did we write this step? Because we have probability of condition probability of xj yk multiplied by probability of yk is nothing but joint probability of xj yk. So this term is nothing but replacement of this and yk. These two, this and this together forms this term. This is the well-known equation, well-known relation. Okay, and this term is as here. So this gives us the conditional probability of x prime provided we know the value of y prime. So this is called the mutual information. That is what we were mainly discussing. So mutual information is represented by this notation. Mutual information I of x prime comma y prime is equal to entropy of x prime minus the conditional entropy of x prime provided we know the value of y prime. Okay, so this is the notation for mutual information. And also this is a definition of mutual information. So what it says, the entropy x prime is the uncertainty about the input before seeing the output. So x prime here is what? It is the uncertainty because we do not know what will be the input. So this is the uncertainty about the input before seeing the output. So this is a general entropy. Now we are talking about the conditional entropy, this term. So that is the uncertainty about the channel input after observing the output. So you see here in a conditional entropy, we know what is the output. Now we are uncertain what would be the input. That is the conditional entropy. So that's again, we are uncertain about the input, but we already know the output. But this is uncertainty about the input before knowing the output. This is the normal entropy. Okay, now when we have a difference here, h of x prime minus conditional entropy of x prime, what is that? That is the uncertainty about channel input, yes, which is resolved by observing the channel output, right? So basically we combine these two statements here. So this is the uncertainty at the input itself, but once we know channel output. Okay, now this mutual information has different properties. We will study 4 properties in this lecture. The first property here is the mutual information of a channel if a channel is symmetric. That is I x prime y prime is equal to I y prime x prime. So this says the mutual information of a channel is symmetric. So here we are replacing x prime y prime by y prime x prime. So this is the first property, the symmetric property. So how to prove this? The mutual information I of x prime y prime is the measure of uncertainty that we know about the channel input that is resolved by observing the channel output, because this is the difference between the entropies. That is what we have seen in the previous slide. And mutual information I of y prime x prime is what? It's a measure of the uncertainty about the channel output that is resolved by sending the channel input. So here we are uncertain about the input. In this case, we are uncertain about the output. It says they are equal, symmetric. So we may try to understand why this relationship is true, or we will try to prove that relation. But before going to that, we will see, because we will be using some terms directly. So before going to that, we will see some background information that helps us in understanding that proof. So here we have some background information. So in a discrete memory-less channel, when we know the transition probabilities, it can be represented as a matrix. I will show you how. So you have some input that is given to a channel and you get some output. For instance, when the channel is represented something like this, and you have some input here, X, and you get some output here as Y. This is Y as the output, and this is X as the input. And this may be a vector. You have many inputs possible. Similarly, you get many output values. For example, in case of binary, these X values can be 0 or 1. Similarly, output values can be 0 or 1, right? Maybe you transmit 0, you get a 0. You transmit 0, you get a 1. Or you transmit 1, you get a 0, and you transmit 1, possibly you may get a 1. So these are the different possibilities at the input as well as at the output. So it's a vector. So this is nothing but the channel. Okay, so this can be represented as a matrix because we know the transition probabilities. What is the probability of sending 0 and receiving a 0? Maybe this has a value p00. And also when you send 1, what's the probability that you receive it as 0? Some value, right? Probability of sending 1 but you're getting it as a 0. What's the probability? Similarly, when you transmit 1, what you get 1, what's the probability, and so on. So if we know these transition probabilities, then it can be represented as a matrix in this way. So what's the meaning here? So this says probability, there is a conditional probability of y naught, first symbol, first output, provided you are sending x0. Okay, then again, then next element here in this matrix, what's the condition probability of getting a y1, provided you are sending x0. That means along this row, if you see, you are sending the same input and you are observing what will be the output, y, right? For instance, you're sending a 0 and at the output you're checking what is the output, whether it is 0 or it is 1 or something else. Similarly here, you are sending a well-known input x0 and you are predicting the probability of getting a 0 here or getting a 1 here or something else here if it is not binary. Similarly, next you are sending the second symbol. We send the second symbol 1 and you check what is the output, whether it is 0 or it is 1 and so on. So whether it is 0 or it is 1 or something else if it is not binary. If it is binary, you have only these two, 4 elements. Okay, so when there are many symbols like j number of input symbols, you have the matrix growing in this way, and k number of output symbols. Okay, so this can be represented as a matrix. So if you see the row wise, we have a common input and their sum is always equal to 1. So probability of sending x0 here, we are sending x0, right? And then we are checking what's the probability of getting y0, y1 and so on. So total probability, when you sum up, this should be equal to 1, right? You are sending 0 and you see what is the output here, and you send a 0 and see what is the output here, maybe 1. Total probability of this and this should be 1. Okay, so this is information is necessary to, because we will be using this idea in one of the equations in the next slides. So that is something like this. When you consider all the outputs 0 and 1 and so on, the probability of getting a particular value for output, provided you know the input, that total summation of the probability is equal to 1. So here the total summation of the probability is 1. Okay, when the probability distribution for any input value, that is xj, that is p of xj, this is the notation for different values of input, then the random variable x is equal to xj occurs with the probability p of xj. That's equal to probability of x is equal to xj. So this is just the notation. So here p of xj is the probability of the input xj. J value can be any of these. In case of binary, it is 0 or 1. And with the help of random variable x, suppose if we appoint random variable x to represent these values of input, then how do we write this probability? Probability of xj, we can write it as probability of x is equal to xj, because x is a random variable that takes the values of xj. Okay, okay, then y is the random variable for the channel output. Then the joint probability distribution of x and y are probability of, I mean, joint probability of xj yk is nothing but probability of x is equal to xj, y is equal to yk. So this is what x is equal to xj. That means we are using, instead of writing the symbols directly, we will be using a random variable to represent the symbol or take the values of the symbol. That's what is written here. Instead of xj here, we are appointing x to take the value of xj. Instead of yk, we are writing y here. Okay, then probability, this joint probability is nothing but the conditional probability multiplied by the probability of the input. This relation we have seen in the previous lectures. So that is nothing but probability, conditional probability of yk multiplied by probability of the input xj. Okay, now we will continue the previous discussion of solving the first property of mutual information. I of x prime y prime is equal to I of y prime x prime. So in these two slides, we saw some background information to solve that first property. Okay, so we saw entropy of x prime is nothing but probability, log of 1 by probability, and that can be represented as probability of the same term here multiplied by this term here, k is equal to 0 to k minus 1, condition probability of yk and xj. So this term is as it is here multiplied by another term, still that is equal to h of x prime, because we have seen that this value is equal to 1. I can show you here, this value is equal to 1, right? When you sum up all these, the value here, that's equal to 1. So basically this term here is rewritten, and we are multiplying here by a 1 here. So the value is not altered. So h of x prime is nothing but summation j is equal to j 0 to j minus 1. That is all the values of input, all the values of output, probability, joint probability of xj, yk, log of 1 by probability of xj. How this has come? We know this, right? In the previous slide, we have seen this joint probability and conditional probability here. Okay, so we get information, mutual information of x, y, k. This is the general equation. It's a difference between the entropies. So that is j is equal to 0 to j minus 1, k is equal to 0 to k minus 1, joint probability of xj, yk, log of probability of conditional probability of xj divided by probability of xj. So again, base rule here. So finally, we have mutual information of x, y prime is nothing but joint probability multiplied by these terms, that is same as the joint probability of y prime, x prime. So our property was mutual information is symmetric here. That's equal to this. That is what we have proved. So we need to remember this base rule here as well as in the previous slide. So that directly gives us this relationship. So that's why in this way we have proved the first property of mutual information, which is symmetric. Similarly, we have other properties such as second property here, the mutual information is always non-negative. So it says this is must be, it can be 0 or more than 0, it cannot be less than 0. That is, mutual information is non-negative. Next property here, mutual information of a channel may be expressed in terms of entropy of the channel output. So mutual information here is equal to the entropy of output minus the conditional entropy. The last property here, the mutual information of a channel is related to the joint entropy of the channel input and the channel output. So here mutual information is what? Is the input entropy plus output entropy minus the joint entropy between input and output. So this is the fourth property. So these are the different properties of mutual information. Of course, these properties can be proved. So this proving these properties is left to you. You may refer the book and try to understand. So basically, we need to know the relation between joint probability and conditional probabilities, similar to the property 1, the proof of property 1. And if you know that, we can apply the similar ideas here and solve these properties. So basically, this is a study exercise for the students. The textbook, the proof is given, and this is a simple proof. So I will leave this to you to understand, study and understand. Basically, this uses the common knowledge of entropy and probability and applying that here. So this is an exercise for the students. Okay, so this is the end of this lecture.